Well, greetings, students. Today I want to spend a few minutes going over a very important relationship. That is the relationship between time and concentration of a drug in plasma or blood. And this relationship really represents the sum total of all four ADME processes on the body. So let's look at this time versus concentration profile. And basically there are two axes that we need to consider, one called concentration and one called time. Now I want to point out to you that time is an independent variable, and we always put the independent variable on the x-axis. Concentration depends on time. That's a dependent variable. So please get used to seeing this concentration versus time set of axes. You'll be seeing those for many years to come, believe me. So if we have to start out with what might a concentration be, where do you think it would start? Well, it would be reasonable that it would start at concentration 0, at time 0. So then, after an oral dose, we would get the drug being absorbed, being absorbed, being absorbed, and being absorbed, and that's called the absorption phase. And then we find that we get predominantly elimination. Now this is called the elimination phase, where the drug is being eliminated or gotten rid of more quickly than it's being absorbed. So that's the elimination phase. And this is an overall representation of a typical concentration versus time profile for an orally administered drug. Now the other thing I want to point out to you is a couple of key pharmacokinetic parameters that are related to this graph. And one has to do with the concentration at which we see the maximum. And this is called, appropriately enough, Cmax. Okay? And then the other parameter we have related to that maximum is the time at which it occurred. And as you might expect, that's called the Tmax. Okay? So we have a time and a concentration at which this peak occurs. Very important. Another very important pharmacokinetic parameter related to this curve has to do with the area bounded by the curve. And this area is often referred to as the area under the curve, the AUC. It's abbreviated as AUC. Very important idea. And basically the AUC represents the overall exposure of the system, the body system, to the drug. It's what you might call the time average concentration. One other important pharmacokinetic parameter that falls out of this results from the fact that you can in general look at a time interval. Say we have a time interval, let's say here, during which the concentrations might drop from x to 1/2 x. Okay? So that interval, and I'm sure you can guess what that's called, is the T1/2, the half-life. Okay? And the same interval during another portion of the elimination phase would also have the concentrations drop by a half again. Okay, so these are some key relationships that we have amongst time versus concentration that you should be aware of. You'll hear more quantitative aspects of this later, but at least this is a beginning. And bioavailability has to do with the fraction of a drug that reaches the systemic circulation. And we can actually determine bioavailability again by using our PK plot of time versus concentration. So if we have an oral dose, as we showed the last time, an oral dose might have concentration something like that, right? And we get an AUC, which represents the overall time average exposure after that oral dose. Well, that's kind of an abstract idea, this AUC. How does that relate to its bioavailability? The absolute bioavailability is a comparison to an intravenous dose. So let's look at an intravenous dose, which of course starts out high because it's dosed directly into the bloodstream. So this is an intravenous dose. So I'm going to write here IV, and then this one here is PO. Okay, oral. And the bioavailability then can be represented this way. F, which is the symbol usually used for bioavailability, equals the AUC for the oral dose over the AUC for the IV dose. Okay, so I hope that gives you a little bit of an idea of a very important use of time versus concentration profiles. We could talk about what would the impact of the concentration be on the therapeutics, on how the drug is actually affecting the body. So as you might expect, if we're in a situation where we have a very high concentration up here, or over a certain threshold, certain concentration over a threshold, what are we going to get? Well, we're going to get toxicity. Okay, toxicity. Now, on the other hand, we may have a certain threshold by which we get therapy, or under which we have no therapy, or I'm going to say it's ineffective. Sorry for the bad handwriting. And in between then we have concentrations which are ideal. These are what are called therapeutic. Okay, so these concentrations here are therapeutic, and you'll often see this represented as we move from pharmacokinetics to pharmacodynamics. The important thing in drug therapy is to stay within that therapeutic range and not to give a dose that is so that is so high that you run into the toxic range, and not so low that you never achieve ineffective concentrations. One way in which we can manage to kind of stay within that therapeutic range, again, let me put more time versus concentration profile. This time I'm going to shorten it just to C versus T here. And let's talk, this time I'm going to compress it a little bit. Let's say we gave that oral dose and it started to go up and then it started to come down, right? But let's say before the drug started to come all the way down, we gave a second dose. Well, what would happen? Now it would go up a little bit higher, right, before it started to come down. And if we get a third dose, that would go up a little higher. And then a fourth dose, and then a fifth dose, sixth dose, and then if we stop, well, it comes down. Interesting situation here. This is a case of repeated doses. So if we're giving a dose, a relatively small dose every day, you'll notice something very interesting. We manage to stay right within our therapeutic window. Beautiful, isn't it? So now, of course, these concentrations here are never observed because we're giving a subsequent dose prior to the actual concentrations coming down. It's just theoretical. So I hope this gives you an idea of how repeated oral dosing could, at least intuitively, you can see how that helps to maintain blood concentration so that you have pretty much consistently within the therapeutic window. Sometimes this is called reaching steady state. It's a kind of a approximation of steady state, where steady state would be a true line, but this is steady state after repeated dosing. And again, you're going to hear more about this from a quantitative perspective later, but I just want you to at least be exposed to it at this stage of the game. Okay, God bless.